Hello, and welcome to our Remote Learning Produce Food Safety webinar series. My name is Ashley Skinner, and I'll be the host for today's webinar. This series is funded by the USDA and is led by our PI, Dr. Michelle Danieluk from the University of Florida Citrus Research and Education Center, located in Lake Alfred, Florida. This project is in collaboration with Florida Agricultural and Mechanical University with PI Dr. Harriet Paul, located in Tallahassee, Florida. Our overall goal with this community outreach project is to develop innovative and engaging remote learning produce food safety curriculum that is highly accessible to diverse growers, particularly small and beginning farmers, in order to equip them with increased food safety awareness and the skills to adopt proven food safety risk reduction practices. To do so, one of our aims is to develop instructor-led workshop webinars to diverse audiences across Florida and the US. Today, we have two FAMU students from the School of Environment, from the FAMU School of the Environment. Joining us in our discussion, welcome Armando Moraine and Walker Marshall. And finally, we have Dr. Keith Schneider from the University of Florida Department of Food Science and Human Nutrition as our featured speaker to teach us about post-harvest water practices. Take it away, Dr. Schneider.
I want to make sure we're looking at the correct screen.
No.
How about now?
Perfect.
Outstanding. Well, thanks everybody for inviting me to speak today. What I'm going to try to do today is introduce you to the topic of post-harvest water. And as Ashley mentioned, this particular topic takes a lot of time. Normally, we'd spend anywhere from an hour to 2 hours on this, and we're going to try to condense that down to a brief introduction and cover the topic in about 20 minutes or so. If you have any questions, you can use the raise hand function or drop a comment in the chat, and we'll do our best to kind of keep up with those questions. So with that, every learning module we present, we'd like to have a couple of takeaways. And for this particular learning module, some of our takeaways are: one, understand why harvest and post-harvest water is so important. We want to get an understanding of how cross-contamination can occur and how we can sort of mitigate that cross-contamination that can occur in harvest and post-harvest activities. And lastly, I want you to understand the use of sanitizers and their safe role in produce processing. So first thing we have to get across is there's really no way to completely eliminate pathogens from produce in the field. Produce is grown outside, and it's not in a very controlled environment. We have animals from mammals to birds to insects, all of which pose a potential risk. We're also not free from blowing dust that could contain particular pathogens. So there's really no way we can get rid of everything. Now, foodborne illness associated with produce, you see some of the numbers, they're fairly high, but on an individual basis, these events are still very rare. So it's one of those things where we're trying to prevent very rare occurrences from happening, and that's what makes working with produce so difficult. What we can do is prevent that contamination, which is usually small when we do get some contamination on produce, from becoming a very large problem. And the use of harvest and post-harvest water really is one of the key areas where we can turn a small problem into a very large problem. Now, if you look at the picture on the right, imagine one of those tomatoes, and again, that is a tomato flume used to move tomatoes from dry field bins to the packing line. Imagine if one of those tomatoes were to have salmonella on it, and individually, if somebody came across that one tomato, it would make one individual sick, maybe a family who would come in contact with that. And while that, again, is tragic, it at least is limited to a small group of people. Now, if I don't properly treat my water or make sure that I take care of all the potential for cross-contamination, say in a flume like this, what can end up happening is the contamination from one particular tomato could then spread to literally hundreds of tomatoes. So rather than one individual getting sick, I now have the potential for making hundreds, if not thousands of people sick. So harvest and post-harvest water use is one of those areas where we're going to try to contain problems, keep them small, and prevent them from becoming a larger problem. Now, when we talk about post-harvest water, and you've heard me already say this, I'm saying harvest and post-harvest. When we talk about post-harvest water use, that includes water that's being used during the harvesting process as well. So this is anything past irrigation. As soon as we go into the field to start removing that produce, again, that's considered post-harvest water use. And we use it for water for all sorts of activities. One of the classic ones is one you just saw in the previous picture, and that was a flume or dump tank. And this is a way we can get tomatoes that are in large field bins transferred to the packing line without bruising. So what we do, rather than dumping them onto a hard conveyor belt, we dump them into these very large tanks of water, which can be anywhere from small volumes, or even sink size water up to about 10 to 20,000 gallons. So there's a lot of potential for cross-contamination in these types of tanks. We can use it in hydrocooling or washing, and this is an image of a hydrocooler where we want to remove the field heat from produce. That helps extend shelf life, aids in maintaining quality. So what we do is we shower the water with very cold water. And that way, again, we're removing that field heat. And again, the potential for cross-contamination goes up here as well, because again, as we use that water, we're reusing it. And again, if we put one contaminated batch through a hydrocooler, every successive batch that goes through there has the potential for picking up that cross-contamination. Another one is making ice. We do use ice in the produce industry. Ice is made in very large quantities and then is shoveled or laid over the top of a rack of produce, and this is called top icing. And when you top produce with an ice, if it's not clean, as that ice melts, that water then contaminates everything in that rack or stack of bins. And again, that has the potential for making things contaminated, and we're trying to reduce that. We also use water to mix up the chemicals that we might add. So if I'm using a sanitizer, I'm usually going to dilute that out with water. That should be clean. I'm going to be making or adding things like a fungicide or a wax coating on produce. Again, if we're mixing that up with water, if that water is not clean, we have the potential for, again, taking very clean produce and then contaminating it by not using clean water. We use it for washing hands, not for everything from the field crew that's harvesting the produce out in the field to the folks in the packing shed. Again, if we're not using clean water to wash hands, again, we have a potential for cross-contaminating that produce. And we're going to use it for cleaning and sanitizing the facilities, and there's a lot of other uses. But again, as we look at all these activities, this should illustrate the fact that if we do not have clean water, what's going to end up happening is we have the chance for cross-contamination, or in fact, spreading contamination, and again, making that small problem into a very large problem. So first we want to talk about is, controlling cross-contamination. And this is one of the major concerns we have in the packing houses or packing sheds. We're never going to remove the pathogens completely. So there's always going to be a potential for small amounts to get through. But if we allow cross-contamination to occur, again, that small problem becomes a very large problem. And it's fairly easy to transfer if, in fact, you let pathogens into your facility. They're easily transferred from a dirty surface to a clean surface, from a piece of dirty produce to a conveyor belt, from the produce to maybe workers' clothing. All these things have the potential for spreading microorganisms. Here's an example. When workers are harvesting tomatoes, they usually will have small little buckets, maybe about anywhere from 3 to 5 gallon type buckets, and they will pick the tomatoes off the plants, and then they have to take the stems off. And what they will do is they'll take the tomatoes, they'll use their thumbs to knock the stems off, or they'll rub them against their shirt. Now, if you imagine if you have a fecally contaminated piece of fruit and you rub it on your shirt to knock the stem off, what ends up happening is that contamination is now on the worker's clothing, and then every successive piece of produce that's rubbed against that clothing has the potential for inoculating or cross-contaminating dozens, if not close to 100 fruit afterwards. So changing clothes, making sure workers are wearing clean clothes every day is a way of knocking down that potential cross-contamination. So is, again, sanitizing at the end of every day, or maybe several times a day. In produce production, we usually sanitize at the end of beginning and ending of a shift. In certain operations in meat and poultry, we may actually have 3 sanitation breaks during a particular day, just because there's a higher level of pathogens concern for meat and poultry. But again, at minimum, many of these facilities are cleaned at least once a day. And again, we'll talk about the water in just a little bit. One of the things, again, in this sort of very limited talk, is we're going to talk about clean water and the water reg as it stands now. And we're operating under the Food Safety Modernization Act, which is signed into law in 2011. One of the major tenets of the Food Safety Modernization Act is the Produce Safety Rule. This regulates all the activities for pre and post harvest activities associated with produce. Now, for water that's going to be used for harvest and post harvest activities, there's a water quality standard that we have to meet. And that standard is no detectable generic E. coli in 100 mils of sample. And what this means is we're not going to be testing for individual pathogen or pathogenic microorganisms. What we're going to use is an indicator organism. And that indicator is generic E. coli. Generic E. coli is found in fecal material from warm-blooded animals, whether that be humans, deer, bunnies, whatever. And if in fact we find generic E. coli, that means we have some fecal contamination associated with that water, and then the potential for other pathogens now exists. So it doesn't mean that we have pathogens. What it means is we have the potential for that. So if we have no detectable generic E. coli, then all those other fecally associated microorganisms are not likely to be there. It doesn't mean that they can't be there, but it's a good indication. And this is why we use indicator organisms like generic E. coli. So one of the tenets here of this rule is that when we have any harvest activities or post-harvest activities, our standard is going to be no detectable generic E. coli in 100 mils of sample.
Dr. Schneider, it looks like we have a question from one of our students.
Yes, Armando, go right ahead. Unmute yourself.
Yes, thank you. I would like to know, like, if there's a specific water source that can be used for post-harvest water, and like, does it matter if, like, is it from the city or from a well?
Great question. So the question is what are the different types of waters that can be used during harvest and post-harvest activities? And there's a couple ones that you can choose from. The first is a well, which is groundwater. Groundwater is usually very stable, especially if you have a well-maintained wellhead. Again, that water is unlikely to become contaminated, especially if it's a deep well. So I can use well water. The other is surface water, which are rivers, ponds, and other types of reservoirs. Those are subject to outside contamination, again, like birds and other animals. So if I'm going to use surface water, I'm going to have some type of treatment process, because I can't guarantee that they're going to be E. coli free. So for surface water for harvest and post-harvest activities, surface water is going to be out unless I have some type of treatment plan. The last option is using municipal water, or water from the city or your tap water. Again, that water is highly tested, highly regulated, and a packing shed. especially one that doesn't use a whole lot of water, can in fact default or use municipal water. And again, that's a very safe choice. But for this activity, again, I have well water and I have municipal water. But usually, unless I have some type of treatment for the surface water, I can't use untreated surface water for harvest and post-harvest activities.
Thank you, Dr. Schneider. We actually have another question from our live audience. It's, if we are concerned about pathogens, why do we not just test for these pathogens and use an indicator test?
Great question. So if I were to test what, I'm going to repeat the question. Why don't we just test for pathogens rather than test for indicators? And in some cases, it sort of makes a little bit of sense. If I were to test for something like Listeria monocytogenes, which is a bacterial pathogen, but it's not associated with feces, it's associated with soil. So I should look for that, because whether or not I have E. coli really has no bearing on whether or not I'm going to find Listeria. The other one might be something like a parasitic protozoan, like Cryptosporidium or Cyclospora, which will survive longer than E. coli. So again, an indicator test probably wouldn't best tell us whether or not those organisms are present or not. So the idea of, well, maybe I'll start testing for individual pathogens. Here's where the problem arises. Again, these things are very rare. And if I start testing for individual pathogens, say I ran a pathogenic E. coli test, I'm not going to detect Salmonella. Okay, well, if I test for Salmonella, I'm not going to test for Cyclospora. If I test for Cyclospora, I'm going to miss hepatitis A. So unless I can test for all of them all at once, and that technology unfortunately doesn't exist just yet, for me to be able to find a particular pathogen becomes more of a needle in a haystack. So at that point, it becomes a lot more difficult and really expensive and burdensome to the farmer. So using a generic or an indicator organism allows us to test for the potential, which is sort of a tried and true method that we've used probably 50 plus years now to give us some comfort level in using a certain water source. So yeah, in an ideal world, I test for all pathogens all the time. Realistically, one, that's too expensive, it's too slow. And again, I have a very difficult time potentially finding those microorganisms in there. So again, it just goes down to a practicality standpoint.
Thank you again, Dr. Schneider, for answering that question. We have very eager students. There's one more question we would love for you to address before you continue the presentation.
Sure, go right ahead.
Okay, since we're talking about water quality, what are the problems that can occur beside microbial contamination, like if you don't use good quality of post-harvest water?
Okay, so what are some things other than microbial problems that we can find in water? Okay, so that's the biggest one that's going to lead to, say, illness or injury in the individual. And that's kind of from a safety standpoint what we're trying to avoid. But there is others. And the most common one that we'd be concerned about is chemical residues that could occur. There's been a big concern of things like pesticide residue and other types of maybe heavy metal contamination or other types of potentially harmful chemical substances in the environment that can get onto a particular food commodity. Now, in the US, something like pesticide residue is highly unlikely. Pesticides are so heavily regulated by the EPA. And their application is so scrutinized that the potential for a chemical hazard such as a pesticide is extremely low. But as long as everybody follows the rules. But that's definitely one that we would worry about. Then depending on where you're at in the previous land use, we also worry about other types of chemical contaminants, maybe from the sanitizers that we're using. So we'll talk a little bit of sanitizers in a couple of slides. But if I'm using a food grade sanitizer, there's really no risk to the consumer because it's already been tested to be shown that it's safe. But if I use a non-food grade sanitizer, there's a potential for those chemical residues to get to the consumer and in fact, maybe cause illness or injury or some cumulative effect over time. So again, besides the biological, the other one that we typically get from water would be a chemical hazard. Rarely would we worry about physical hazards at this point, but really chemical and biological are two main ones. All right. So anyway, let's get back to the talk right now. And again, that standard again is no detectable generic E. coli per 100 mils. And really this is any activity, again, during and after harvest. Again, we have different rules that you'll hear in another webinar concerning irrigation water and pre-harvest. But yeah, all those activities during harvest and anything that comes in contact with food contact surfaces, making ice, hand washing, sanitizing our facilities, we're going to want to have that water meet this standard of no detectable generic E. coli per 100 mils. So what do we use water for? And this is kind of an interesting thing. We use it in a lot of different ways. We can use it in a single pass, which is again just maybe hosing something off in a very small operation, or a spray bar. We can use it in batch or recirculating tanks, which means we're going to reusing that water over and over again. But here's a couple of things to consider. One, as the produce safety rule is written, I do not have to use a sanitizer. So whether I'm using single pass water or recirculating water, a sanitizer is not required by law. Now I'm going to tell you that it's almost impossible to maintain that no detectable E. coli, generic E. coli in 100 mils of sample without using a sanitizer. But by law, a sanitizer is not required, but it's highly recommended. And we'll go over a couple of reasons why. The other thing to keep in mind, it's not on the slide, is that you're not legally washing the produce. You're preventing cross-contamination when you're using a sanitizer. Now, if I use a sanitizer and I'm rinsing produce off with a spray or in a tank, am I going to get that produce cleaner? Yeah, probably. But legally, really all I'm doing is preventing cross-contamination. And that's really, I know, a subtle difference between the two, but it's an important one because again, we can never guarantee that even if we're using a sanitizer, that that produce is going to be 100% pathogen free. So from a legal standpoint, we're only going to say that that sanitizer is at an adequate level to prevent cross-contamination. But just remember, it's not required, which is kind of strange. But again, it's highly recommended. And one of the biggest reasons why we recommend it is for the potential of biofilms. Whenever I give this lecture, people always talk about, well, if it's so important, why isn't it regulated? And it has to do with who regulates what with food. But the potential for, again, a small problem to become a big problem really increases when we talk about the introduction of biofilms into some type of packing environment. Now, all of you have some type of biofilm probably in your homes right now. Not probably, absolutely in your homes. If you have pets at home and you've ever felt the bottom of your pet bowl and it's nice and slimy, again, that's a biofilm building up on the bottom of your pet bowl. And again, all it is water and a little bit of animal backwash. And there's enough nutrients there for microorganisms to develop a foothold and start growing on the bottom of that bowl. If you have a pool and you've ever seen the walls or pool go green, again, that's basically a biofilm. If you've ever taken a sink apart, and I often do this with students in my class, take your finger and run it around the rubber stopper in your bathroom sink or kitchen sink, and you'll notice that black kind of slime or goo that comes off. That's a biofilm that is built up into your pipes or around your drains. These biofilms are extremely resistant to sanitizers. Think about all the chemicals that you're running down a bathroom sink: toothpaste, mouthwash, soap every single day, but yet there is a persistent, thriving colony of microorganisms that again line those pipes that you have in all through your house. And if you've ever taken apart a U-joint in a bathroom sink, you will know it's covered in a brown, slimy layer of microorganisms. Now, most of these biofilms are benign, which means they don't contain any harmful microorganisms, but some pathogens can form their own biofilms and others can sort of hitchhike into an existing biofilm. And this happened or was thought to have happened at a cantaloupe operation known as our kennel of operation out in Colorado. It was one of the deadliest outbreaks in U.S. history. I think 30 people died, several hundred people got ill. And what had happened in this particular packing shed, packing cantaloupe, Listeria monocytogenes, a particularly nasty pathogen, became established within the facility, believed to be in biofilms. And when investigators went in and swabbed all through that plant, what ended up happening is roughly 50% of all the surfaces were positive for Listeria monocytogenes. And what thought happened was that they had improper sanitation procedures in place. They had equipment that wasn't very cleanable to begin with. And in fact, once biofilms get formed, the normal sanitation procedures that you would use are not going to be effective anymore. So you may have a sanitation standard operating procedure that works just fine, but if you neglect regular sanitation, what will happen is what worked one week won't work the next week if the biofilm gets established in that facility. So once a biofilm gets established, it can be very persistent. They can be resistant to sanitizers that are normally effective, but are no longer effective because the biofilm now has a protective coating that is shielding these microorganisms from the sanitizers. And it also increases the likelihood of these often benign biofilms from picking up or harboring pathogenic microorganisms, and then now they become potentially harmful. So one of the reasons we're talking that you don't have to use a sanitizer what we want you to is so even though you don't have to use one, you don't want to build up a biofilm in your plant. And this way, again, by using a sanitizer regularly, you're less likely to build up this contamination on the surface of your equipment and throughout your facility.
Dr. Schneider, it looks like we have another student who has a question.
Sure, go right ahead.
Thanks, Dr. Schneider. My question is, if you get or suspect a biofilm has developed, what can be done about it?
Okay, so if you suspect a biofilm, what can be done? Great question. Biofilms are, again, really resistant to sanitizers. So there's a couple of strategies we can use. One of them may be to rotate the type of sanitizers that we use. You might be using a chlorine-based sanitizer, which are very effective, but not really good against biofilms. And maybe once a week, I would use another type of sanitizer like a peroxyacetic acid or PAA type sanitizer. And that's one way by rotating the different sanitizers. If a biofilm starts to get established, rotating a different type of sanitizer might help break that up. If you do have an established biofilm on a surface, really the best way to get rid of it is basically elbow grease. Go in there and scrape it off. If you've ever had a pool and it's gone green and you shock the pool with chlorine, and then the next day it goes green again, you wonder, well, I put all this chlorine, why did it go green again? Because you had a biofilm on the walls of that pool. You really need to go in with a brush and literally scrub every inch down. In your facility, if you end up with a biofilm, you can go in there with brushes, low pressure, maybe heat or steam to help break it down, or again, or rotate a different sanitizer in there and help break up those biofilms. So one, I guess the best strategy is not to let it develop in the first place, but if you do suspect one, again, go in there, you can rotate sanitizers, break the equipment down, and literally scrub it off and start new. And that would be probably the most effective strategies. Okay, moving on. So speaking of sanitizers now.
Thank you. So it looks student might have another question to ask.
Really? Go ahead.
You are muted, Walker.
You just talk about sanitizer, and then I would like to know why cannot household bleach be used as a sanitizer?
Okay, great question. So why can't household bleach be used as a sanitizer? That's a tricky question, and here's the reason why. Household bleach or sodium hypochlorite, the chemistry, sodium hypochlorite is a great sanitizer, and it's one of the chlorine sanitizers that I'm going to mention right now. The reason that we don't use household bleach is for the first bullet item you see up here. Household bleach is labeled for use in the home for laundry, and it's the concentrations that are on the bottle. Its level of purity is such for home use. Any chemical that is going to be used for food contact, or cleaning food facilities has to be made to a certain standard, and thus is going to be labeled for use for ag water, washing produce, or washing food contact surfaces. So typically food grade chemicals are made to a higher standard than household chemicals. So that's one reason. The chemistry itself, sodium hypochlorite, is in fact just fine. And sometimes people will use sodium hypochlorite and the term bleach interchangeably. And really they are. Household bleach usually is sold at a concentration of 5 to 6%. And while that same concentration is used in industry, typically most industrial sanitizers are slightly higher concentration, maybe 15% or higher, just so we're not shipping a whole lot of water around. But it's really for the impurities. If you think about laundry, the bleach we use in laundry, sometimes it's lemon fragrance or rain fragrance. While that may make your clothes smell good, it probably not really good to get that on your food. We don't know what chemicals that they're using to generate those fragrances. And plus, there's other impurities that might be in that bleach product, like heavy metals, cadmium, nickel, lead, that we don't want to have on contact our food or our food contact surfaces. So again, great question, and leads me to the first bullet point here. Any chemical that you use for agricultural use, for food contact, must be labeled for use on produce. And again, every chemical that we'll see will have an EPA registration number on it. It will be labeled for its intended use, like ag water or produce washing. It will tell you whether or not it can be used and whether it requires a potable water rinse afterwards. Something like a sodium hypochlorite requires a potable water rinse after. It's going to tell us whether we can use it on a particular surface, whether it's food contact, use it for cleaning walls, floors, whatever. So different chemicals have different uses, but again, it has to be labeled for that intended use. Now, chlorine-based sanitizers, and there are a couple of them. One of the most common is sodium hypochlorite, which is a liquid form we call bleach. Another chlorine base is calcium hypochlorite, which is a solid form. If you've ever seen pool tablets, or the ones we use for swimming pools, that's also is a chlorine base. We could also use something like chlorine gas. The interesting thing, whether I use chlorine gas, calcium hypochlorite, or sodium hypochlorite, the main active species that we're going to get is hypochlorous acid, which is going to be the active species in water. And I'm going to give you a couple of slides on specifically that reaction that occurs. But there are many other sanitizers out there that are not chlorine based. There are some formulations that are acceptable for organic produce production. Something like a peroxyacetic acid or hydrogen peroxide again can be used on organic produce and are very effective and are really good antimicrobial agents. There's no one perfect sanitizer out there, because again, there's a couple of things that we try to take into consideration. One, we want it to be cheap or inexpensive. Again, we don't want to spend so much money that we're not making a profit anymore. Two, we want it to be safe to use. And we don't want it to be so effective that it starts corroding our equipment. And we also want it to be environmentally safe and safe for our workers. Every sanitizer has some trade-offs. Ones that are gentle on the environment may be more expensive in cost. We make it a little bit less cost effective. Ones that are super economical, again, might actually end up corroding our equipment. So there's a balance to be struck, and depending on the type of produce you're washing, the potential risk, and the equipment in operation, again, you're going to make an informed choice of which one to use. But again, there's no perfect choice. And we usually tell the farmers and packers that use the one that works for them in their situation. Now, the efficacy of any sanitizer is really going to be based on several factors. One is its concentration. How much am I going to be using? Typically, the higher concentration of a particular chemistry, the harder it's going to be working. The temperature that I use it at is also very important. Chemicals tend to react faster when it's warmer. So if I have elevated temperatures, my chemical reaction may be quicker, be more efficacious. The problem is I'm going to run through that chemistry a little bit quicker. It won't last as long. Again, increase the cost. The quality of the water, whether the water is hard water, contains minerals or not, will affect the efficacy of certain sanitizers. The pH, honestly, how acidic or basic the water is one of the more critical ones, especially when we're using that sodium hypochlorite. And we will, I'll show you a couple of slides because honestly, that's probably the most common sanitizer that's used out there. And again, that's the bleach, the same chemistry that's in bleach. But if we don't actually monitor the pH level of the water, the efficacy of that solution can be greatly reduced. So again, we want to take particular importance or attention to how acidic or basic that water is. Really, as to be an effective packer or trying to do any type of strategy to knock down the potential contamination from microbes, you really need to have a handle on, again, all these different parameters of how they're affecting your sanitizers that you're choosing. So I'm going to go on now. Oh, we have another question. If you want to unmute yourself, go right ahead.
Okay, thank you. Since you're talking about the factors that affect the efficacy of the sanitizers, you're talking about concentration, temperature. Do you think the time of application can be a factor that affect the efficacy of the sanitizers as well? And if yes, how?
Sure. Okay. So the question is what about contact time? And how does that affect efficacy? And that's a great question. So certain sanitizers, as a matter of fact, a lot of the sanitizers will give an actual time to get a certain reduction in water. So the longer something's exposed to a particular chemical, the more time it has to react, and therefore it can be more efficacious. But in produce processing, especially water applications, we're fighting a battle a little bit. So we want the sanitizer to be most effective. So the thought would be, well, let's leave it in there longer. The problem, the longer we leave it in the water, the more chance we have of water infiltrating or being absorbed into the produce, and that makes the problem worse. So we're always striking a balance between getting the maximum concentration time with the minimum amount of infiltration. So again, the longer I have exposure to a particular chemical, the more likely I'm going to have infiltration, especially in a fluming operation. Now, if I'm on a brush bed where the piece of produce is not submerged, I have to worry about that less. So then at that point, the longer it goes through, the more contact time I'm going to have, and maybe increase the quality by knocking down some of those organisms that are not associated with pathogens, but more quality, things like mold and spoilage organisms. In that case, a brush bed might be a better option. If I'm doing a fluming operation, my goal is, again, not to clean the produce. Remember, I said legally, we're not washing the produce. Our goal is to prevent cross-contamination. So we want to make sure that we're preventing cross-contamination. And in that case, it's really not the contact time that's the most important. It's really probably the concentration. So contact time is important, but typically in a water operation, we're trying to limit the amount of time that produce is actually in contact with the water. Because again, that raises another issue. So we're constantly fighting that battle between letting the chemistry have enough time to act versus causing something more deleterious like water infiltration into the produce, which can bring pathogens from the outside into the inside. And then once they're on the inside, then we lost the battle at that point, because once they're on the inside, we can't get them out, and then they have a chance to now increase. Right. Another great question. So let's talk about hypochlorite chemistry. And this is what I was just mentioning. Again, sometimes people call this bleach, but really I break chlorine chemistry or hypochlorite chemistry into three main types. The first is sodium hypochlorite. Again, that's the liquid form that we call bleach. We have the solid form, which is calcium hypochlorite, and then we have chlorine gas. The interesting thing, again, is when I add any of these three to water, the resulting chemical that is produced is HOCl, or hypochlorous acid. And this is the efficacious agent that we're trying to produce. This is what's actually doing the killing. Now, the interesting thing and why pH is so important for its efficacy is HOCl doesn't exist by itself. It exists in equilibrium. So as I put this in water, depending on the pH, I'll have a certain percentage of my chemistry in the HOCl, or hypochlorous fashion. And then I'll have a certain percentage in the OCl minus form, which is a hypochlorite ion. At 7.5, I'll have a 50-50 split. As I lower the pH, I drive the equilibrium more to the hypochlorous acid side. So I'll end up getting more hypochlorous acid, which is what we want, because it's about 8 times more effective than the OCl minus form. So at 6.5, just 1 pH unit lower than the 50-50, what will happen is I will have 90% in the hypochlorous acid and only 10% in that OCl minus. Now, the opposite is true when the pH goes up. As the pH raises, say 1 pH unit to 8.5, I'll have 90% in that OCl minus form and only 10% in my HOCl active form. Now, both of those forms, the OCl and the OCl minus, are in fact registered as free chlorine. So if I put in 100 part per million free chlorine and I'm thinking I have a lot of disinfection chemistry going on, if I don't monitor my pH carefully, what's going to end up happening is I could have the vast majority in the OCl minus form, and I'm getting very little efficacy. This is why pH is so super important. And most packing house operations where a chlorine-based sanitizer or a hypochlorite sanitizer is being used, typically an acidulant is added to make sure that that pH remains at 7.5 to 6.5. We don't want to go lower. Again, if I went to from 6.5 down to 5.5, I can get 99% in this active form. And it's, well, why wouldn't we want 99%? That sounds like a really good idea. The problem is, as we get lower and lower pH, we're now in an area that's getting so acidic that that pH is going to be very corrosive. We're going to have a very highly reactive chemistry that is going to basically degrade any metals in that system a lot faster. And then also, as we drop the pH even lower, what's going to happen is we'll start eluting chlorine gas, which is a potential indoor air pollutant. Again, it can be very dangerous to produce chlorine gas. So we don't want to acidify too much, but we want to acidify it to where, again, we're getting between that 90 and 50% range. And that target is really 6.5 to 7.5. Now, I always get the question, well, why don't we just add more chlorine? Why do I have to worry about measuring pH and adding an acidulant? Why don't I just keep adding more chlorine? Well, if you notice, the HOCl comes from sodium hypochlorite and water. Now, when I put those together, I end up with HOCl, but the chemical that I haven't put on the slide is NaOH. Sodium hydroxide is the other chemistry that's left over, and that's a base. Sodium hydroxide is in fact a base. So the more sodium hypochlorite I add to the system, the higher the pH goes. The more I add, the less effective it becomes. So that's the crazy part. The more bleach or more sodium hypochlorite that I add, the less effective the chemical treatment becomes. So in this case, that's a classic example where more is not better. It's actually better to use a judicious amount of chemistry, make sure it's properly pH, and get the maximum amount of efficacy. I'm also using less chemistry, which means I'm going to be saving money. I'm also going to be helping out the environment because I'm not dumping all that excess chemistry and just using and wasting a whole bunch of very inefficacious sodium hypochlorite and just throwing it down the drain. So this is where, when we talk about pH in post-harvest water, why it's so important. And again, if you've ever worked with pool chemistry before, you're always measuring your chlorine concentration and you're always measuring your pH. And this is why. If you don't, the amount of chlorine and the chlorine in any type of hypochlorite chemistry situation is not going to be efficacious. And you might get a whole bunch of chlorine smell and absolutely no killing power. So again, pH is super critical. Other factors, and again, and it depends on which chemicals that we're using. The water hardness can play a big part in how efficacious something is. The level of organic material in the water is also very critical. So if you're using water in a recirculated system and you keep putting more and more material into that same bath without changing the water, you're going to build up a whole bunch of organic material, and any type of sanitizer you're using is going to be less effective. During the beginning of the day, the water is very clean, and I may be only using maybe an ounce for every 10 gallons. By the end of the day, I may be using an ounce for every gallon of water I have to treat, because I have to overcome that organic load in that water. And that's one of the reasons when we're using recirculated water, and even though the regulation says I don't have to add a sanitizer, it's a little bit kind of nutty that I don't, because again, how am I going to prevent the potential buildup of E. coli or fecal material in that water when all that organic material that's being washed off is being recycled over and over and over again? Imagine a bathtub, you take a bath, and then somebody else has to use that same bathtub, and then somebody else, and somebody else. And you're the 100th person to get to use that bathtub. You're not going to be happy. You'll be happy if you're the first person, but not if you're person number 100. And I don't care how much soap you put in there, that water is going to be dirty. And the same thing happens when you're processing in a recirculating system, is that a lot of organic matter goes up, and it's going to be harder and harder to guarantee that water is clean. Now, we do have to balance that in certain areas like Florida. We do have restrictions on the amount of water that we can use, and therefore we have to balance how often we change that water. Because again, water is a premium here in Florida. We don't want to just waste water, because we have a limited supply of fresh water. Plus, but we don't want to use it so long that we're using a lot of chemistry, because that water is going to have to be returned to the environment somehow, and we don't want to return it with a whole lot of chemistry in it, because again, that could deleteriously affect the environment. So we don't want to impact the environment by dumping a whole bunch of chemistry. So it's a balancing act. The other thing that we worry about is temperature. Again, if the water is too cold, if we're processing maybe winter vegetables up north, the water may be very cold, and chemistries that are fairly efficacious when they're about 80, 90 degrees may not be working so well if we're at 50 or 60 degrees. So again, how fast they react, again, by reducing that, if that temperature is too cold, may slow down any type of efficacy. But again, if it's too hot, we may be burning through the chemistry a little too quickly. Even though we have good efficacy, we may be using a lot of chemistry to maintain because of that high temperature. What's being washed is also important. Again, if I'm washing something like maybe apples or tomatoes, which are grown again on vines or on trees, those are a little bit easier to clean, and I may be able to use that water a little bit longer, and I may be able to use a little less sanitizer. If I'm processing things like carrots or any root crops, or maybe leafy greens, which are grown close to the ground, and I'm bringing a lot of soil into my system, again, I might be changing my water a little bit more often, or I might be using a sanitizer that's a little bit more resistant to the level of organic material. Sodium hypochlorite is affected greatly by the amount of organic material in the water. Something like a peroxyacetic acid can tolerate organic material and still have efficacy a little bit better. So maybe for root crops, I might want to use something like a PAA. Maybe for vine and tree, I might want to use sodium hypochlorite. It all depends. And then lastly, the type of organism we're trying to protect against. Certain organisms are more resistant than others, and some, it doesn't really matter what you do. Bacteria and viruses are fairly easy to inactivate, the ones that are going to make us sick, but there are some protozoans, parasitic protozoans, the things like Cryptosporidium and Cyclospora. Quite honestly, they're called oocysts. The infective stage of those particular protozoans are very resistant to things like chlorination. So again, in those situations, the type of chemistry may not be effective at all. You may need to use some type of ultrafiltration or some type of filtration to get those out. So these are also other figures that you want to pay attention, again, as if you're going to be processing produce. So getting close to the end here, things I want you to consider. One, if you're going to use a sanitizer for any food operation, but in this case specifically produce, it must be EPA approved. You can go home right now, look at any sanitizer bottle you have, and you're going to find an EPA registration number on any sanitizer, even in your home, because they're labeled for home use. If you're going to use it in a food processing environment, it has to be labeled for its intended use, and you'll see right on there for produce wash or for ag water treatment. it will be listed on the side of the bottle or box that the chemistry is coming in. So again, EPA registered and labeled for its intended use. Those are the two biggies. We also have a use solution of how high or how much you're able to use. Again, using it within the, according to the manufacturer's recommendations, what it's certified at can be safe. And it goes back to the earlier question of chemical hazards. A food grade sanitizer is food grade as long as you follow the instructions. If you start using it to excess, it then can become a chemical hazard because residues might make it to the consumers. Next, important things to consider, having standard operating procedures for any operation, whether it be sanitizer use, how we monitor and calibrate our equipment, how we store the produce, written SOPs really are helpful to make sure that any of these procedures, which some of them can be fairly complex, are done correctly each time. Certain things are it can be a little bit easier than others. One, just taking temperatures may just be something as simple as using a clipboard and just looking at a chart. But changing pH or sanitizer concentration levels might be a little bit trickier. Having written procedures prevents or lessens the amount of mishaps that occur. Anytime you apply any type of procedure, you should monitor it, and you need to keep keep records. So a lot of times people will try to cut out as many steps as possible. But again, if I'm going to monitor my chlorine chemistry and I'm going to monitor the pH, then I have to have a procedure, an SOP for those. And again, I should be keeping records of those operations because again, that's going to be super important. And then lastly, when any type of food safety plan, whether again, we're dealing with produce or any type of food, always have a corrective action plan. Have a plan in place when something goes wrong. Inevitably, something will always go wrong. So having a plan to react to that before it occurs, that way you can effectively manage that situation is critical. So if you're going to have somebody go monitor the sanitizer concentration and it has to be above 10 part per million, what do you do when your employee comes back and it's at 8? That's a corrective action. You need to have a plan in place. Maybe you segregate that product, maybe you dispose of it. And then you need to get the chemical level back to the right concentration. So typically you have really a two-step on corrective action. You fix the problem, then you figure out why it happened in the first place, and you do things to prevent it from happening ever again. But again, always have a plan or corrective action in place before something goes wrong. You don't want to be figuring it out on the fly. So some take-home points and summaries. The reason for this entire talk, harvest and post-harvest water has the ability to make a small problem into a large problem. Of all the things that we talk about, this is the one where when we hear about big outbreaks, it's usually because something happened at this stage. And water is one of the biggest vehicles that, again, makes headlines, unfortunately, for all the wrong reasons. Remember, despite this entire talk, sanitizers are not required by the produce safety rule for either single pass or recirculated water, which sounds crazy by the time we get to all this and all the things that can go wrong. But again, by law, they're not required. As we stated, they're highly recommended. Again, we want to avoid things like biofilms, potentially and reducing that cross-contamination that can occur in a normal operation. If you use any sanitizers, you want to make sure you know exactly how they work. Again, if it's a sanitizer that is affected by pH, you need to know that. If it's affected by water hardness, you should know what the water hardness is. If organic load's an issue, you need to know how frequently you're going to be changing your water or how much makeup water you're going to add to keep everything working according to plan, and then you maintain that efficacy throughout. So regardless of what you do, you have to understand the chemistry. And again, I usually spend an hour on that one aspect of it. But yeah, really understanding what sanitizers you're using. And if you don't know, typically your chemical supplier is going to help you out. Again, it's in their best interest to make sure that you're using the best chemical that has the best chance of success for that particular operation. Again, if you're using chlorine-based sanitizers, really go over and understand how pH affects that chemistry. Remember, for those activities, right, that we discussed today, that during harvest and post-harvest activities, the criteria is no detectable generic E. coli per 100 mils. Again, we're using an indicator organism, and we're taking a very large sample. So again, we're looking for no detectable generic E. coli in 100 mils of sample. There is no perfect sanitizer. You have to analyze the situation, the type of water, the type of equipment you have, and the type of produce you're going to be washing. And again, choose the one that's right for your operation. And lastly, if you're going to have any type of operation for any business, you should keep records. Standard operating procedures, again, make sure that you do things correctly. If you don't have a standard operating procedure, it's like not having a recipe for a very complicated meal. Inevitably, it's going to taste terrible. So again, in this case, if you don't have standard operating procedures, inevitably something's going to go wrong. Somebody is going to take a vacation, and the new guy is going to come in and possibly mess things up. So again, SOPs are great for making sure your operation runs successfully. Make sure you keep records. Again, you're going to use those, one, to fine tune your system. Two, if you ever have to any legal proceedings, to make sure that you've done your due diligence and you've done everything correctly. And all of these, again, are all for preventing or reducing cross-contamination. Remember, we're never going to get the level of contamination down to zero, but we do want to keep those large problems as small as possible. All right, that is the end of my presentation. If anybody has any additional questions, I'd be happy to answer those.
Well, it looks like we have no other questions that were added in the chat. So we just want to again thank Dr. Schneider for coming today and sharing with us about post-harvest water. If you have any additional questions, please feel free to email me or email Dr. Schneider. His email was found on the first slide. If you could pull that up for us one more time. His email is...
Hold on one second. I got rid of it there, but I'll pull it up. And I'll drop it in the chat as well.
All right.
There we go.
As you see here, his email is keiths29@ufl.edu. Thank you again for participating and attending this webinar series.